Question 2. The diagram below shows the circuit used to measure the current voltage IV characteristics of an electrical component X. So that's this one over here. On the diagram above, label the ammeter A and the voltmeter V. So your ammeter is always in series with the device because you're measuring the current. So the same current that is moving through the device needs to move through the ammeter, so it's in series. It's a very low resistance device. We say it's got negligible resistance. Your voltmeter is always in parallel. Now this is a very high resistance device. That means that there's just about no current that actually flows through the device. So it'd be something like that. Mark the position of the potentiometer that will produce a reading of 0 on the voltmeter. Now that would be here. If we had it coming in over there, so it would be over there. Now the reason for that is that this piece of this wire over here, I'll mark it in green, because it's just cable, a conductor. This will have 0 resistance. So when the current is flowing here, it's either got the choice of going through the resistor or 0 resistance. So all the current will go through the 0 resistance, and then it will go through the resistor, the potentiometer. So at this point over here, if you've got the dial, the potentiometer there, this is when you're going to get maximum current. So that would be maximum current. This point P will be minimum current. And it says here, the graph below shows the current voltage IV characteristics of two different conductors, X and Y. Now, just for interest's sake here, for X, this is an ohmic conductor. You can see here that it's a proportional straight line graph going through the origin. For Y, it's a non-ohmic. One can see here that your current and your voltage are not directly proportional. So state the value of the current for which the resistance of X is the same as the resistance Y. Now remember, R is equal to V over I. It's the ratio of your voltage for your current at a specific time and situation. So at this point here, at that point there, we're going to have our R being the same. So the current will therefore be 0.4 amps, because we can see that across there, 0.4. Your resistance, R is equal to V over I. We have got, it will be 10 volts, so it's going to equal 10 divided by 0.4, and when we divide that, we're going to get 25. That will be 25 ohms. Then it says, describe and suggest an explanation for the IV characteristics of the conductor. Now, this is I against V. So, if I redrew that to V against I, we would get something like that. So, as one can see, you haven't got a directly proportional relationship between V and I. The slope of this graph, which is your change in V over your change in I, is actually getting greater. So as you increase your voltage, you're not getting a correspondingly same increase in your current. And the reason for that is that your resistance is probably increasing. And it's probably increasing because the temperature is increasing. So the reason for this, an explanation, is basically because this is a non-ohmic conductor. We are probably getting an increase of temperature and therefore leading to an increasing resistance. And because I is equal to V over R, as your resistance therefore is increasing, you are not getting the same increase in your current. So I hope you'll be able to describe and explain from that explanation. Then moving over the page here, it says the two conductors X and Y are connected in series with a cell of negligible internal resistance. The current in the conductor is 0.2 amps. Use your graph to determine the resistance of the Y value of the current and the EMF of the cell. Okay, so we've got 0.2 amps. We're going to need to go back to our diagram and have a look at that. So we got 0.2 amps. If I go across here at 0.2, I can see here that I have got a voltage of, for my X, of 5, and here for my voltage for my Y of 2.5 for that. So we can now go back to our diagram. Let's go back to there. Hopefully we'll just remember that. You've got the diagram in front of you anyway, so that shouldn't be too bad. Alright, so let's just draw the diagram here. We've got a cell, and it's in series with this X and Y. And we're going to have here, remember this is the potential difference here of for my X was equal to 5 volts, and for my Y was equal to 2.5 volts. And we have got a current of 0.2 amps. So the resistance for Y, R is equal to V over I, would equal 2.5 divided by 0.2, and that will equal 12.5 ohms. And the EMF of the cell, well, it's going to be 5 plus 2.5, that will be 7.5 volts. 7.5 volts. Because, as it says over here, it has got negligible internal resistance. So it's having no resistance, no energy loss in the cell itself. So all the energy that is being used up in the circuit is being created by the cell. So the EMF, the total energy that has been produced by the cell, will be the 5 plus the 2.5.